All right, my friends, welcome back to PreCalc. I'm here, Mr. Who, talking to you today about the polar coordinate system. So we're going to talk about polar coordinates a little bit here. We're not going to go too deep into it. We're going to basically touch on the basics of how to use the system and how to plot points. Okay, and then we'll be moving on. I'll also show you what it's used for, really. Okay, but we are not really going to delve that deep into it for sake of time. And I think that's pretty much how we're going to go about it. So we're going to look at the basics. That's what's going to be on your IP as well. We'll look at those later too. And also going to bring up Desmos later to talk about more about the polar graph and what it looks like and all those little features. So let's get started. First of all, what is the polar coordinate system? What is it? Okay. Well, simply put, the polar coordinates are a grid system, so just like our Cartesian plane, that better observes circular and orbital motion. Okay. Polar coordinates are a grid system that better observes circular and orbital motion. What do I mean by circular and orbital motion? Well, hopefully those two words indicate some sort of roundness, okay, some sort of cycling. So it kind of lines up with what we've so far talked about in trig, that is a rotation around the plane, and the unit circle. Those ideas are obviously better observed, and you would probably describe them as a circle, okay, or something that happens within the 360-degree rotational circle. So we can use polar coordinates to better describe those shapes and pieces we've been describing with Cartesian the whole year, basically, or the whole semester, I should say. Okay, so when we talk about this, there are a couple of things we need to know. First of all, okay, it still uses an ordered pair. Still uses an ordered pair. So let me go ahead and kind of remind you what an ordered pair is, because you may have forgotten what it might look like. Maybe know what it is, but you forgot the name. Remember that an ordered pair is something that has an x and a y coordinate. Right? X coordinate, y coordinate. This is the Cartesian version. Okay. As in the traditional version we've all grown up with and loved since Algebra 1 or whatever. Okay. Here's the polar version. Okay. We're going to have an r in our first slot and theta in our second slot. So our polar coordinates will actually use this thing called a radius. Okay. And it will also use this other idea, theta, which if you know, have been paying attention the whole class, theta refers to an angle. Okay, so that's the main difference between our polar coordinates and our Cartesian coordinates in terms of their ordered pairs. Okay, so what exactly does the radius describe? Well, let me change my color here so I know what it's tied to. Radius describes distance from the pole origin. Okay. So if I'm 5 units away from 0, 0 in terms of length, that's my radius. You can also kind of think about this as the word magnitude. Okay. So if you remember that from our vectors section, radius actually pretty much just tells us what's the length of our vector. Okay, right? What's the length away from the origin that our vector, our point, is in the plane. Next up is the theta. Okay, whoops, I actually cap locked that. The theta. Theta describes the angle of rotation. Okay. Hopefully this is nothing new to you. We've been doing this the whole semester, where if you recall, this out here is 0 degrees, and when I rotate this way, okay, you'll be going up positive until you get up to like right about here. This is 90 degrees, right? And if you keep going this way, you'll hit 180. Okay. Same thing here. Nothing has changed. That is the same thing. But we're mostly going to be using radians for this, so please remember how to convert between those. All right, let's pop over to Desmos to actually look at this and also describe some points that I'm going to give to you, okay? All right, so I'm here on Desmos. This is the classic Desmos you load up anytime you look it up. Okay. But there is actually a feature that will allow you to change this normal-looking plane into a polar coordinate plane. All right, so take a look. You can click this gear, or I guess it's a wrench, more like not a gear. The wrench up here Let me move myself also so you can actually see what I'm doing. Okay. The wrench up here will let you see exactly the settings. You might notice that under grid, there are two different types. There's this one that looks very square, boxy, and this other one that looks like a circle, right? Or like a more of a spider web kind of deal. If I click on this, wow, look at the difference. I'm gonna move myself back over here. Now I have a coordinate plane that is using the polar coordinate system. And you can see there are a lot of differences between this and the original plane. Whereas the original plane had a positive x, positive y, negative x, negative y axis, this doesn't really have that. So let's look at these together. I'm going to use my colors that I used on the notes to identify what is going where. So if we look at our system here, we have a bunch of little numbers. Okay. We have a bunch of little numbers. Sorry about that. Had to change my recording so I can actually annotate on this. There are a bunch of little numbers dotting the axes. So that's right here. 2, 4, 6, and 8, right? So you can see those, and it goes on to 10 and free on. Okay. That's, it doesn't really seem that out of the place yet. That's like our positive x-axis, right? But if I look at all the other axes, you'll notice that it still uses the same 2, 4, 6, even in the negative side, if you're thinking traditionally with a Cartesian coordinate plane. Very bad circle there. I don't know what Zoom's doing. Come on, Zoom. And close enough. Okay, so when we look at these numbers, they're all the same. That's because this is our radius. Okay. In this case, this is the length it takes to get from the origin to wherever that area is in the graph, in the coordinate plane. So if I'm talking about this 2, then this right here is 2 units, 2 radius. Okay. All right, that's pretty cool. Next, let's talk about this blue ring. Okay, we're going to use this blue to cover the ring. Out here, you can see different areas with pies. Okay. And of course, this refers to our theta, okay, our angle. And hopefully, that doesn't look too bad to you. Hopefully, you've known, or at least played along with delta math and radians enough to know that these are the radian equivalents to our known degrees. That would be 30 degrees here. We got 60 degrees here. I know it kind of messed up there. We got 90 here, and so on and so forth. So this is essentially just a big old circle. Okay, a big old circle of a graph, where the red numbers indicate the radius length, and the blue numbers indicate the angle in the plane. Doesn't seem so bad. Now, let's do a couple of examples real quick using our ordered pair coordinates in this type of system. If I gave you the coordinates 4 and pi over 3, okay. Remember that r, the radius, is this number, and theta, the blue number, is pi over 3. So if I were to graph this thing, first I would need to locate our 4. So I go out here, da-da-da-da-da-da-da. Here's 4. Okay, so now I've located my 4 radius. Next, I need to locate my angle. That would be up here, right? The pi over 3. Then I simply need to consider this whole circle where the radius is 4. That would be this guy. Very shoddy. Okay. But think about this as the circle. I also kind of missed. And where that circle's angle at pi over 3 is, and that's the point I'm talking about. So that would be this guy right here. And I will actually erase my original dot. Okay. So why does this indicate our connection there? Why is that a point? It's because it has a radius of 4. That's the length right here. And it has an angle of pi over 3. Which I guess that should have been in blue, but same difference. Okay, cool. Let's do another quick example. I'm going to show you another one. Let me use another color. Let's do purple. Okay. So for example, if I were to do, let's say maybe 5, and then I'm going to do 7 pi over 6. Okay. Well, I'm going to read it in terms of radius and theta. So radius 5, that means I'm looking at around, let's say, this is 6, so 5's got to be right here. Okay. I'm looking at about this area, okay, which it could also be over here, the same part of the same circle. And I need to look for 7 pi over 6. Well, here's 7 pi over 6. I'm following this ring, that is the 5 ring. Here's my point. Easy, right? Okay, that's our polar system. All right, now I'm back here. Now you might be wondering, okay, great, Mr. Hu. I saw you do that thing with the graph. I'm still not really sure how to tie it with what I know about the plane already. So here are a couple of ways to convert between the two planes. Okay, I'm going to use this as a very important kind of thing. We're going to call this key conversions. Okay. So as long as you know the representation in one plane, you can actually get to the representation in another plane. Here's the first key conversion. It is that x equals r sine theta. X equals r, sorry, it should be actually cosine theta. That's my bad. R cosine theta. That's r times cosine theta. You want to be a little more particular about that. So if you need to translate from our Cartesian x into our polars, this is how you're going to do it. R cosine theta. As long as you have 2 out of the 3 variables in this equation, you should be able to find what you're looking for. Typically, that means if you have r and theta in your polar, you can go backwards and find out what your x is. If you only have your x, well, you're probably going to have to work together with your y in order to get whatever's left. Okay. Next up is y equals r times sine theta. Okay, well, that's pretty self-explanatory too. There's that idea again that x and y are tied to cosine and sine. So bringing that back one more time. Okay, you're going to keep seeing it, so you better get used to it. Again, just like with the above x statement, you can use this to convert between your y and your r theta. Finally, this is one that everybody likes, loves, knows more about than you ever really paid to know about. It's our favorite Pythagorean theorem, except this time we're using x and y as our sides. Okay. Remember, x being a fully vertical or fully horizontal movement and y being a full vertical movement helps you describe the two sides of a right triangle. And of course, what's the hypotenuse of that right triangle? It's the radius, okay, of whatever point you're trying to plot in polar. So there we go. That's the last conversion you need. Alrighty. So when we convert back and forth, which you can see the videos in Delta Math on how to do those. We'll also do some in class. You will be able to see how this all plays out. Okay. Most of us are more comfortable with Cartesian, but we're going to try to get a little comfortable with polar. Okay. I think it's a very nice system to really think about. Now, let me show you a couple of applications of this whole system. All right, sorry, real quick before I do that, before I show you the graphs of what this is actually used for, let me actually draw a representation in the plane about those conversions, because I think that's probably going to be important. So let's just take any old random line. So here's my line, and I'm going to put a point at the end of it. So here we go. Okay. If you are thinking about our x's and y's, here's the y part, right? This is our y. And down here in the blue, I'm going to use this dotted line as my x, right? So those are the two parts that would correspond to Cartesian. Okay. But when we talk about polar, that would be this guy right here, which is our r. And I'm going to use pink for this one. This guy right here, which is our theta. Okay. Where hopefully all those conversions made a little more sense to you, because if I take the sine of theta, okay, sine of theta is opposite over hypotenuse. Y over r. Y over r equals sine theta. I multiply both sides by r. Y equals r sine theta. Wow. Groundbreaking, right? Okay, so that's the visual representation of how the conversions work. Same thing with x. If you do x equals r cosine theta, you'll find that cosine theta is actually x over r. That's using our trig identities, trig function, sorry. And knowing that we can just multiply both sides by r, you'll get r cosine theta equals x. Okay. And finally, you can hopefully see this is an x squared, y squared, r squared situation. Okay, now let's actually get down to graphing the actual things I wanted to graph. All right, so I've got the setup. You can go sit back and watch how this works. Okay, but the way polar coordinates work is that typically, just like with Cartesian equations, you have x on one side and y on the other. But in this case, you're using r and theta, right? So let's take a look at our equation here. I'm going to mess around with it and show you what the shapes created look like. Right now, it's a very basic circle, with a radius of, looks like 0.5, based on the length of this. And it's got like a miscentered, it's centered on whatever this is, 0.50 instead. Okay, but as I change these, okay, we'll take a look at it, observe how this works, and then I'll talk a little bit more about why this is important, so to kind of look at it. So first, if I go ahead and change our A, you can see that as it goes negative, it goes on the other side, and as it goes positive, it goes to the front side. All right, so far, nothing too impressive. I don't know what Mr. Who's trying to show you. But now let me show you what happens when I mess with n. Okay, when I mess with n, which is inside our cosine theta, here's what happens. Ooh, look at that. Okay, so I will probably stop it on one of these bad boys. Give me a sec. Okay, so this is a shape that is circular, okay, and it cycles, okay, depending on our theta. Remember, theta can only go through 2 pi before it starts to cycle over again, okay, as cosine would anyway. So this is kind of the same deal. Okay. As you graph and as your theta gets larger and larger, you'll never go outside of whatever this curve looks like. Now, as to why it's important to really observe, I'll let both of these play out now so you'll see how that works. Okay. Why? If the first thought that popped in your mind was like, wow, that looks pretty flower-like, then that's exactly the point. Okay. The exact point of this polar coordinate system is so that mathematicians and scientists and whoever else is in the field can observe flowers using some sort of graph. Okay, they don't have to actually go find the flower in the wild, okay, to maybe research it in terms of geometry anyway. Okay. So that's why I kind of mentioned if you're an art interested student, polar might be useful if you ever get a chance to work with it later. Okay. But of course, as always, math is supposed to represent the real world, okay, in numbers and a system we've created. So the polar coordinate system is just another convenient way for mathematicians and scientists to look at and observe the geometry of the real world. Okay, and I'm sure if you search out polar coordinate graphs, you might be able to find some really wild and wacky ones. I wouldn't be surprised to see them show up on our slides when I put it together. So keep an eye out for those. I think it's really fascinating, but we're not going to go this far into it. You don't have to worry about making these graphs. You only have to worry about the basics. That's converting between Cartesian and polar and understanding what the polar coordinate system is. Now, this is getting pretty lengthy now, so I'm definitely going to let you go. We'll talk about the examples in class. I will see you then. This is Mr. Hu, out.